Hello, Bobcat. I'd like to give a little tutorial on acids and bases. Um, this might be long, so it might take a couple of videos, but here's the first one. Before I get into this too much, I just wanted to cover something from a previous chapter that we have not gotten to yet. And what that is this concept of equilibrium. Um, if you'd like to learn more about this, it's in the chapter previous to the acid and base chapter that we're doing now. So when we talk about chemical equilibrium, this is kind of what the name tells you. Uh, when you have a chemical reaction, right, where is the reaction located? Is it all products? Is it more products than reactant? Is it more reactant than product? Uh, where does the chemical reaction lie? Really think about here. Um, so you can think about a chemical reaction as having reactants on the left of the yield sign, right? And then having your products to the right. Okay, so you have your reactants on the left, your yield sign on the right. And really what we've kind of been talking about all year long is having these reactants and they make the products. End of story. But really in a lot of reactions, that's not what happens. Some reactions are reversible, where you can change direction, right? Now these would become the reactants, these would become the products. But a lot of reactions are kind of somewhere in between. Okay, and so what we have to talk about here is basically of their, how much of the reactant exists, how much of the product exists, how much is it changing from one to the other. Okay, and so what we do to think about this is um, we talk about how much there is of something, meaning concentration a lot of times. A word that we've talked about in class we learned last year in terms of concentration would be the number of moles, right? Would be the amount. Or concentration would be the moles per liter if it's in an aqueous solution, or so how many moles of the substance are in, right? We talk about this as molarity, capital M. I think we might have used this one as well. What we're going to look at it is concentration is in a mathematical equation. We're going to look at how much of something there is in brackets, and so you could put, well, there's of my reactants, there's 1 molar, right? The concentration of it. Okay, and so what we're going to do is we're going to put this into a mathematical equation where we're going to say every reaction has some constant, right? And so we can say we don't use C, we use K for constant. And so this constant would be this reactants, the concentration of the reactants. So how much of the reactants are there compared to the concentration of the product. And so we can actually take the product. So we can actually take this concentration of all the products and divide it by the concentration of all the reactants to get some constant for every reaction under certain conditions. Okay, this would be called the equilibrium. So how much reactants exist, how much product exists. Okay, and so we use this ratio, this fraction of it, to see where the reactant is. So if you talk about this equilibrium constant, this K, being a very large number, that means you have a lot of products compared to reactants. Okay, if this equilibrium constant is a small number, that means we have a lot more reactants than products. Okay, and usually reactants, sometimes they just go and they stop. You can measure how long it takes. You can measure how far it will go. That's thermodynamics. Kinetics is how fast it goes. We're talking about equilibrium, though. A lot of times some reactions are in what's called dynamic equilibrium, where they are moving. They're reversible for one, and they're moving from the reactants to the products, or the products to the reactants continuously. So you can think of a lot of chemical reactions as trying to run up. Here's your dynamic equilibrium, where your products are running up and your reactants are running down, or the stairs are running down, and so you have this amount that is kind of stuck there. So it's an equilibrium. We're not going to get too much into this. You might be saying, well, how does this relate to acids and bases? Okay. Well, it does very much. You have to think about where this equilibrium is for acids. Okay. In fact, that's what makes a strong acid versus a weak acid. Okay. Here's a list of the strong acids. You saw these last year or 2 years ago, and this is them. Memorized them. I think we memorized them when we did reaction stuff, right? And these are the substances that are made. Okay, so what makes an acid an acid? If you notice, they all have hydrogen in common, and that's the definition of an acid. An acid has hydrogen in it. And when you put it into water, that hydrogen dissociates. Okay, and so you get this anion that's created. Sulfuric, hydrochloric. Sulfuric is the only diprotic, meaning there's 2 protons, diprotic. The others are monoprotic. They all have 1 hydrogen. So this has 2 anions that it can actually dissociate 2 hydrogens from the sulfate. I don't know if we did any acid naming. I can give you some stuff on acid naming if you need it. But if it's not on this list, then it is a weak acid. All other acids are weak. Okay, so what does that mean? What happens? What's the difference between a weak acid and a strong acid? Okay, here's a couple of examples. Hydrobromic acid, on this list here, HBr. It is a strong acid. So if you notice, you have your equilibrium constant, you have your yield sign, it has to be in water, right? And so we get this concentration of our products. Okay, what makes a strong acid is that hydrogen and the ion dissociate to completion. That means that when this is in water, hydrogen bromide, or here's nitric acid, when it's in water, there are no reactants. This doesn't exist. This doesn't exist. It exists 100% as the reactants. 100. So this has 100. Strong acids have 100% dissociation, or very close to it. Okay. Weak acids don't have 100% dissociation. It's the difference. When you have iodic acid, right? It exists in the reactant form. HiO3 actually is floating around in the water, and that has some anion floating around in the water. Okay, here's the Kas for some of these this list of weak acids, meaning at close to room temperature, at 1 molar, this would be the concentration. Right? If you notice, all these are really small. That means it's mostly reactants. Okay, and that's the difference between a strong acid or weak acid. Weak acids go both directions, right? It exists not in 100% of the products. It exists in some reactants, some are products. Here I've drawn it out. This is acetic acid. I drew it out where it lies. It lies more to the left, or as reactant, the big arrow there, than it does as products, the little arrow there, right? It's definitely reversible. Okay, and it's the amount that it dissociates is related to its Ka, right? In the beginning of the video, I was talking about Keq, that's the equilibrium constant. This is the Ka. It is the acid constant, right? How much does the weak acid dissociate? Ka for strong acids, of course, would be 100, a molarity of 100. I mean, not the really, the Ka would be the concentration, the molarity of that acid, right? The concentration would be whatever the molarity of the acid is. Those are acids. So bases are similar to acids, but instead of all the bases having hydrogens, they all have OHs, or they essentially what they do is they usually have a hydroxide, or they give away, they pick up the hydrogens rather than give away the hydrogens like an acid does. Here's a list of the strong bases. Easy to memorize. These and every other base is weak. It is basically the alkali metals and alkaline earths. So it would include lithium, sodium, potassium with hydroxide, lithium, sodium, potassium with hydroxide, and barium, calcium, strontium. So these have to be calcium, strontium, barium, and these two as well. So almost all of the, except for beryllium and magnesium, they make strong bases. And obviously, well, hydrogen actually does make a base as well, as we will see. But that's the difference between a strong and a weak acid.